Ziatdinov, and I'm originally from Russia, but I live and work outside. So this research was a little bit generalized because I was not expecting that I'll visit this conference and I'll give a talk in here. So the title is Visualization Methods in the Mathematical Modeling of Interpolating Curves with Monotonic Curvature Function. So the title was slightly changed, as I said before, and so this is a joint work with my friend Norimasa Yoshida from Nihon University in Tokyo in Japan. So first of all, let me tell you about the table of contents. So I will start with some simple introduction. Actually, I will explain why we are interested in curves with monotonic curvature function. So why do we study them? Actually, it will be told in terms of visual perception of geometrical objects. So we will go to the quality criteria for curves we use in a shape modeling. And then I will speak about the polynomial and rational splines and their limitations. So in the field of shape modeling, computer graphics, and computer design. So then I'll pass to analytic curves, which we use and we study them here. And then, I will show you some visualizations of well-known functionals which we use in the field of geometric modeling. And I will tell conclusion and so on. So let's start. First of all, I would like to tell you that usually geometrical shapes of the outside world objects, they hide and undisclosed emotional and psychological, artistic, aesthetic, and shape generating potential. So they may attract you with their shapes, or they can make you to be afraid of something. So it means they can cause fear as well as a variety of other emotions. So it suggests that living beings with vision perceive geometric objects with an information handling process. So actually our vision is very similar to the vision of chimpanzees, for instance, as it was investigated by Japanese scientists recently from Kyoto University. So we perceive the shapes in a very similar way, especially convexities and concavities of the objects. So the first guy, actually, he was a psychologist, Fred Atnev. He suggested that the concepts and techniques of information theory may shed light on a better and deeper understanding of visual perception of geometric shapes. So he made some experimental research. So he was studying closed contours, and so actually this is one of the contours he was showing in his research. So he concluded that information along visual contours is concentrated in regions of high magnitude of curvature as a positive being distributed uniformly along the contour. So he said that if a human sees any kind of objects, so first thing that is his eye is attracted to these points. So this kind of points, these, and so on, right? So actually, in some cases, we have a positive curvature here, right? In some is negative. And he also stated that actually negative curvature points, they bear more information. It can be described in terms of quantitative information function, or he was calling this surprisal function. So actually, these points are very important for human vision. So the other points are not that important for us because we're not attracted by them. So our eye is not caring about this. It's a kind of information handling process. So as I said before, so a very important concept here is the quantity information function, or so in the field of visual perception they call this a surprisal. So it can theoretically help us to explain the concentration of information on the visual contours. So based on this, we first, in our work entitled Visual Perception, Quantitative Information Function, and the concept of the quantitative information continuous splines, we have proposed new types of splines for visualization of shapes from a given set of discrete data without adding any in-between points with curvature extreme. So if you have a set of data, so now you know that data is everything, right? So we live in the world of large data sets. So if you have a large data, so in the case of quantity continuous quantity continuous, the quantity of information function. So in the case of our splines, we use curved segments with monotonically varying curvature. So we are not interested in some oscillations of curvature function. Why? I will explain this later. So we construct splines using this kind of curved segments. So the curvature monotonicity should preserve. So this is very important. So recently we have proposed a new class of such very general curves which were called superspirals. And so in our case we defined the curvature function in terms of the tangential angle as a Gaussian hypergeometric function. And so these are the conditions for its complete monotonicity. So the function is completely monotonic. So we can generate so many shapes with so that we are interested in. So unfortunately we couldn't find an exact analytic representations for these parametric curves. And we use some numerical integration methods like Gaussian, Cronworth, adaptive methods, and so on. So we can robustly compute them. So on the other hand, so in what we're interested here, so only if you take into account the monotonicity, so it would not be enough to achieve the high quality of shapes we can use in computer graphics or in shape modeling. So we call planar and space curves which are used for industrial purposes. So usually they provide some functional characteristics of an object. So we call them functional curves. So this is a little bit different than from functional. So it means they use some function. They're used to make something, right? So we have proposed the universal quality criteria for curves actually. So the universal requirements for shape quality of the functional curves can be proposed regardless of the specific details of the designed object. So we can use these kind of shapes everywhere, starting from ship hull design and to airplane design and so on. So this is a kind of universal quality criteria. So we are interested in high quality curves here. And one of the issues is here is, so the order of smoothness should be not less than 4. So order of smoothness should be not less than 4 or higher. So the absence or minimal number of curvature extreme points, so absence is preferred in fact. But if you know that in the case of splines, so we have so many control points, right? So we cannot avoid of them. So the next one is small variations in the values of curvature and its rate of change. So this is an important part as well. And small value of the potential energy of curve. So we have to minimize, or we have to find some values of the functional in a given area of where the curve is existing, or the regions of curvature monotonicity and so on. And finally, so we since we study freeform curves, right? You know that usually splines they have, so they're called freeform curves, right? Because they can be easily modified, right? So we just move the control points, and the total shape is changing, right? So we call them freeform curves or freeform shapes. So we propose that, so to get a high quality shape, so we have to apply anesthetic analysis from the standpoint of technical aesthetics laws. So it's a very complex analysis here, and usually artistic designers, they have to use around like 12 or 13 spatial principles to make them to be aesthetic. So the next is, now I would like to tell you slightly about polynomial ratio splines and why we try to avoid of them. So you know that there are lots of different kinds of splines in fact, right? Even starting with B-splines, actually B-splines were first used by Nikolai Lobachevsky, actually a little bit in different form, but he was using them in generating the paths for celestial bodies. So Usually people, they don't mention about this, but he was the first who was used the B-splines as well. So the next type is NURBS, or non-uniform rational B-splines. So this is a rational function, the rational parametric curves. So they are very flexible. We can change the shape in a very flexible way. So if you move one point, so these arrays will not much change. So only в окрестности точки. I forget how to tell this in English. So the next is like, you know, the Bernstein-Bezier curves. Actually, they're very popular and very useful. So also Pythagorean photograph curves. So they were invented recently by Reda Faruqi at California State University. So in this case, is arclet is given as a polynomial. Actually, the arc length of the curve is given as a polynomial. They also have some interesting properties and getting more and more popular. So all these were actually polynomial or rational splines, and the next is isogeometric splines. They are also kind of well known and famous, and I think one of the famous guys in Russia who was studying them was Boris Kvasov from Novosibirsk. So in the field of isogeometric splines, they usually try to use spatial algorithms to preserve the monotonicity. If the data is monotonic, so of course the spline should be monotonic, right? But B-splines or NURBS are not always monotonic. There might be some oscillations, so we have to avoid all this. So you can achieve some convexity and other properties. Actually, isogeometric splines are very useful, especially in approximation theory. So besides that, the fact they're very useful and very popular, so we believe that so rational and polynomial splines, they have many limitations. They have many limitations, and so usually people, they close their eyes on this. So one of the limitations is so difficulty in the control of curvature function. So it's very difficult to control the curvature. So as soon as you move one of the points of the spline, so you don't know what will the curvature function itself. It can happen anyhow, so we don't know. So the next is I think very well-known Runge phenomenon. So if you use a high degree polynomials, you can get oscillations. So the next is actually a big problem in the field of computer graphics. So if you want to connect different patches, if you want to achieve a smooth connection between patches, which, for example, share one vertex, so there might be some complex algorithms, or they may not exist. So still, we have some problems if the surface is degenerate. If the surface is degenerate. So we cannot construct such an algorithms for making the connection to be smooth with some order of smoothness. And recently, so in my articles published in the Scientific Visualization Journal, so I concluded that so if you use polynomial splines, so you can get a distorted visual perception of the modeled object. And I have shown some pictures in here. So this is a duck, right? So we use the same input, right? The same input points. And so here I increase the degree of polynomial. So from 3 to 4 and to 5, right? So even I made some funny caption here. So the duck which turns into pterosaur, actually, the duck turns into a dinosaur. But the initial points are exactly the same in every case. So if you have some curvature extreme, it can bring you to some different problems in different areas of engineering. So the first one is so the presence of curvature extreme points on the airfoil. So you know what does airfoil mean? So it's a cross-section of the 8-lane wing. So cross-section of the 8-lane wing is called airfoil. So it leads to pulsation of the medium, and it increases the drag of an airfoil, and it can cause flow separation. as well as increased pressure on the airflow. So you can get some additional pressures, which we don't want, right? Because it can crash your wing as well. So if the curvature extremes are present on the curves of the car body surfaces or in some architectural shapes, so it will lead to effect of distorting mirrors. So it will look like not so beautiful. So we call this effect of distorting mirrors. So the availability of curvature extreme can cause the unjustified beating of a pusher and eventually lead to early rear of a mechanism. So it's a kind of mechanical engineering. So if some mechanisms are moving, right, so they can break fastly, right? So if the shape is wrong, if the shape is not optimal. And finally, so it can cause the necessity of superfluous braking and acceleration, which ultimately increases the energy to move a vehicle. So in different areas, different problems arise. So if there are some problems with shape, if it's not optimal, so it means we'll have some problems. So here, I have modeled the airfoil using NASA 2412 airfoil data. I was using NURBS in here. So usually, computer designers, they prefer using NURBS. Why? Because they're very flexible. Using NURBS, you can model any kind of surface, especially in the field of ship hull design. Some surfaces can be very complex, and many degenerate patches may arise. Many degenerate patches may arise depending on the initial data, initial experiment. So, but they are still flexible and useful. So, here I think I was using around 24 points, something like this, and I was analyzing the curvature values here. So these red lines are showing the curvature values. So, of course, you can see there are some problems. The curvature function is not that smooth enough as you might expect it. And even here, I have enlarged this area, so you have that curvature values become even negative, right? So it means you will have some area like this. And if the airplane is moving with a fast speeds, right? So there was some pulsation of the medium, pulsation of water or air or gas or plasma. So it's better to avoid of this kind of regions. It's better to avoid of these regions. And still, so we don't have good algorithms which will help you to generate splines with very high quality. So we have so many limitations and we have some constraints and so on. So, but we'll try to do something, and then I would like to explain you about some other analytical curves which we use to generate different kinds of splines. So we don't like to use polynomials because they do not satisfy high requirements. They don't satisfy our high requirements. Maybe they are good for approximating function, right? But they are not working in computer graphics. So if you think in a more deep way. So actually there are many kinds of curves, and the most popular of them are elastica, I think, is one of the old types of physical splines which actually were using in a ship hull hundreds years ago, right? But nowadays it's not used because it will help you to generate only one optimal shape, right? But we need to get something different, and it's not satisfying for the experiments we get from industries. So the next one is a conics. Actually, they show better results than polynomials in the case of airfoils. So we can construct some curves with like a C5 class function. So it's very good for us, in fact. But still, in the field of conics, right? So some of our criteria are not satisfied. So conics have some problems. So the next one are spirals. Actually, there are lots of spirals. You know them better than me probably. And recently, in 90s, Professor Harada from Wakayama University in Japan, so he started to study the shapes of natural world objects. So first he was analyzing the outlines of butterfly wings. So he was getting some data and analyzing this information. So he concluded that most of the curves in the wings of the butterflies, they have some relation here. So in the logarithmic scale, so this is the radius of curvature, and this is radius of curvature divided by its derivative by the arc length. So he concluded that these are almost linear or approximated by line. So this how the curves, which actually they were called aesthetic curves before, because actually they invented some law of nature and bring this in terms of equations, right? But then actually, since the equations have a linear graph in this logarithmic scale, they were named as logaesthetic curves. Actually, Professor Carlos Sequin from California University, he suggested this name. So these curves are very useful, and so many companies, like for example Ferrari or some Japanese car makers, they use these curves to generate kinematic surfaces for their car hoods or car roofs for car body design. So that's why you know that Japanese cars are one of the most sold cars in the world, right? And but you see that in our cars you will find some corners, right? So they're not smooth enough. So then, of course, we were trying to develop some interpolation methods using logaesthetic curves. Actually, we have found the analytic equations of such curves, actually. They have a little bit complex representation, and so these equations are represented in terms of incomplete gamma functions. But we can robustly compute them as well. So no problem with the fast computation. But we have some problems with continuity, so we want to increase the continuity of our splines. So that's why in 2012 I have proposed new curves which were called superspirals, and so as I said before, I was using Gaussian hypergeometric functions to generate the curvature as well. Unfortunately, we couldn't represent them in terms of some other spatial functions, but we tried to use Gauss-Kronov method for integration. So, okay, so this was the first types of analytic curves we use to generate some high-quality splines. So the next one is in our recent work published in the Journal of Computational Applied Maths. So we have proposed an extended sequence of Maclaurin. So you know that extended sequence of Maclaurin is a planar curve whose equations in the biangular coordinates are given by this one, right? So what we have in here is 1 minus t to the power of n times alpha. Alpha star is initial angle. So this is the initial angle in here. And this function is defined in terms of t to the power of m times b star. So b star is the initial angle at the end point, or tangential angle, you can say. So in the biangular coordinates, so all the curves are defined in terms of, I don't know how to say this, but you can say this, angle functions in terms of parameter t. So usually, for example, in the case of Bezier curve, t is changing from 0 to 1. So here is the same. So in this curve, so t is varying from 0 to 1. So this is the start point and this is the end point, and you get an interpolation curve as shown here. So the sequence of Maclaurin itself, it has a linear graph in biangular coordinates. So this is a sequence of Maclaurin. But we are using these shape parameters. Actually, if you increase the values of n, so it will pull the curve towards the side of a triangular envelope. So it's a kind of shape factor which will modify the shape. So we have also proposed, actually we have proven our proposition saying that, so to get convex interpolating curve in biangular coordinates, so functions alpha and beta should be monotonic. So we have proven this proposition in our manuscript, so if you're interested you can check. So the functions should be monotonic here to get a convex shape in Cartesian coordinates. So before I told you, right? So we use different factors to get the high quality shapes, right? And minimization of some functionals is actually playing an important role also. So here in geometric modeling, we often use the methods of control theory to get some to smooth the spline or to get some more attractive shape. So especially potential energy functional, which is given by this equation. So we integrate by the arc length here. So the curvature square, we minimize it, right? So this is called minimal energy curve, or MEC. Or we can also minimize the variation energy functional, which is given as this equation. So the curvature, first of all, so we have a derivative here, and then put into the square. So what are the difference here? So if you minimize the potential energy functional, so it will, so the curve will bend the least while passing through a given set of points. So bending will be the least. In the case of variation energy functional, so it will bend as uniformly or as smoothly as possible while passing through a series of points. So there are actually, in geometric modeling, we use some other functionals, especially for surfaces and space curves, right? So if you're interested, you can refer to the work of Morton. Actually, Professor Sequin from California University, he was his advisor. So you can find in this dissertation. So this is the example of a minimal energy curve. This is the example of a minimum variation curve. So all of them are defined by the same direction of tangent vectors here at the initial and final point. And finally, so I would like to show you the visualizations we get with my Japanese friend. So this is the sequence of Maclaurin, while so shape parameters are equal to 1. So high values of functionals are shown with warm colors, and small are shown with cool colors, like blue and so on. So this is how it looks like. So sequence of Maclaurin, and so this is the variation of the visualization of variation of the energy functional. So the picture is a little bit interesting. So what do we have in here? So actually, in our case, so this is the simplest cases. We define a box. Actually, we took some simple case, like 3 by 3 box, right? So we have placed 2 points, right? 2 control points in here. So, and the third point is defined by the directions of the derivatives here. So, tangent directions, right? So, if the point is our, in this region, in the red, right? So, the values will be high, right? So, the values of the function will be high. So, we have to avoid these regions. So, we have to place it somewhere here inside. So, in this blue region. So you can see that color is everywhere is blue, but in fact it's not. Our eye cannot detect the difference between blue colors. So it's actually not blue everywhere. Our eye cannot detect. So if you bring this image to some, like a Photoshop, and you will try to fill the pixels, right? Actually here, every point is defined by 1 pixel. So this is a high quality image. And you will see that you cannot fill all this area. So there might be somewhere. Okay. And finally, so I would like to show you, this is another sequence of Maclaurin with another parameters. So this is monotonicity regions. If you place a point in here, you will get the monotonic curvature. If also, no meaning, we are not interested in such curves. So we're interested in high quality shapes. So this is another type, and finally I would like to, okay, this is a good example. So actually this area is very large, or some other values. And finally, I would like to show you for a quadratic basic curve, actually I was talking about. So the areas are very small. So the areas are very small. So if you place a control point here, so it will have a monotonic curvature, right? But if you place it outside, so you will get nothing. So this will be out of our interest. So we work on in these regions. So we want to combine all these all these criteria and to find the best curve, the most attractive, most aesthetic with minimum values of energy functional and variation of energy functional, and of course it should have a monotonic curvature. I think this is all what I wanted to tell you, so thank you very much again, and these are my contacts.
Any question or comment? So your curve is not polynomial function.
No, we avoid the polynomials. As I said before, so polynomial splines, they are not satisfying high requirements of aesthetic design.
So the spline
Right.
is, the curve is polynomial.
No, it's not polynomial. It's not a polynomial. It's a piecewise defined function, but it's not polynomial. So we use some analyticals actually. But we try to avoid the polynomials because they are not satisfying high aesthetic requirements.
So you have some explicit expression of the function?
Right, we have. So in the case of, for example, log aesthetic curves, so the parametric equations like xt and yt are defined in terms of incomplete gamma functions. So we have exact equations as well. So in the case of sectrix of Maclaurin and extended case, of course we have. This is very simple. So you can use cosine functions and go to Cartesian coordinates. The representation is very simple, and so here monotonicity regions are very, very large. So actually this region is never ends, so you can go to infinity. So you can define the tangent directions as you want in this region. So the angles will be less than pi over 2. So for now it's maybe the best curve in terms of monotonicity regions. So we couldn't find anything better for now.
Any more questions? If no, thank you.